Hi guys, welcome to the video going through the total water hardness using EDTA. So guys, in this experiment we're looking to measure the total hardness, and total hardness of water is measured in terms of calcium hardness and magnesium hardness. There are two ions that cause hardness, and to do that we need to use this special reagent to titrate them against, and that reagent is called EDTA. Now, its full name is something, unfortunately, you guys do need to know, and it's up here, so I'm going to take my time pronouncing it, and I've said this to some of you before, I always like to break it down, okay? So, I would go ethylene, diamine, tetraacetic acid, EDTA. Now, it's very rare that they will ask you to name this, but it is on the list that we do need to name it. And this EDTA complex reacts with your calcium and your magnesium ions. It doesn't react with metals such as sodium and potassium. So if your water has other metals in it, it's not necessarily going to react with them. It reacts with your calcium and magnesium ions, and it kind of wraps itself around them and it makes a complex. And this complex then takes them out of solution. So essentially by doing this titration, you're removing the water or the hardness from the water. And when you've all of the hardness from the water removed, i.e. when you've all the calcium and magnesium ions removed from the water, the indicator, which in this example is our aerochrome black tea, which can also be called solochrome black tea, changes colour. So when the water is hard, we have this lovely wine red colour, and when those ions are removed, it goes to like a lovely blue navy colour. That's the brief outline of the theory of the experiment. We've already gone through the method and procedure in class. What I'm going to do now is go through the calculations. These are a rough sample of results, guys. We have our rough titration and our second or third titration figures. Now, don't forget, we never use our rough titration as to calculate our average. We only use our accurate titrations. In this instance, our 22.2 and our 22.1. So our average is 22.15. And remember, in your titrator or your titer, that is corresponding to your EDTA. And EDTA is what we know most about in this titration. We know how much we've used and we know its concentration. We've used 50 centimetres cubed of our water, but we don't know the concentration of the water, and that's what we're looking for. So as always, we start off with what we know. We know that we have 0.01 moles of EDTA. Now that moles is moles per litre. Moles per litre is moles per 1000 centimetres cubed. And don't forget, we want to use centimetres cubed because we need our answer to be in centimetres cubed. We divide it by what it's in, which is 1000, and we multiply it by what we want, which is 22.15. And when we do this, we get an answer with a lot of zeros, 0.00002215. So that's moles in 22.15. That's how many moles we actually used in the experiment. We then need to look at our ratio. And in this experiment, our ratio is 1:1. So if we have 0.002215 of our EDTA, we must have the same amount of hard ions in our water sample, which is 0.002215. Now, if you flick back to our results, you'll see that we used 50 centimetres cubed of water. So that number of moles, 0.002215, is in 50 centimetres cubed. What we do then is we calculate our moles per litre. So we go about it the same way, 0.002215, and we divide it by what it's in, and it's in 50 centimetres cubed. Now, if my question was asking me to complete this and get 1 centimetres cubed, this is where we'd stop. But I want our answer in litres, so we're going to multiply it by 1000. And when we do that, we get 0.0043 moles per litre, so capital M. Now, in this question, guys, we want our final answer to be in ppm. Now, ppm is milligrams per litre. So our first starting point to getting that far is to get to grams per litre. When we talk about water hardness and stuff like that, we ideally think that all of the water hardness is caused by our calcium carbonate. If that changes, it'll be given to you in the question, but this is the compound we assume is causing the hardness, so this is the compound we calculate our relative molecular mass for. So as always, you go to the front of your exam papers or your log tables to get the mass numbers of each of these. So calcium is 40, carbon is 12, oxygen is 16, and we multiply that by 3, which is 48. And when we add those three numbers together, we get 100. So we take our previous answer, our answer in moles, which was our 0.00443, and we multiply that by 100, and we get 0.443 grams for 1 litre. We don't want that though. We want it in ppm. So our final step is to calculate the ppm, or parts per million, which is milligrams per litre. So to convert from grams to milligrams, we multiply by 1000. So we take our 0.443, we times it by 1000, and we get an answer of 443 ppm. And it's really important that we use ppm to make sure that we're given the right units in this question. Okay, finally guys, I'm just going to go through the questions relating to the experiment. So why is it important that the reaction is rapid, and why is it important that it goes to completion? Well, if our titration is not going to be rapid, it's not going to be very accurate. If our titration doesn't go to completion, it's not going to be very accurate. If we're going to have to use loads and loads of chemicals and get a really, really large volume of EDTA being used, it's not going to be accurate. If we try to keep those volumes low so that our experiment happens quickly and the colour change happens quickly, it means that we're being really, really accurate, and so that we can help calculate the concentration of our unknown solution. Question 2. How could the presence of other metals affect our result, and other metals, suggest other metals that could be in the water? So other metals such as sodium and potassium can be in the water, but these do not react with the EDTA. Other ions can, for example, aluminium or iron ions present, they can react, and that will give us a really, really high concentration of hardness. So we'd have a really, really large hard water figure there. So while EDTA measures hardness, it doesn't distinguish between temporary and permanent hardness. So this question is asking you, how could you show that there is temporary hardness there? Or how could you, what compounds cause our temporary hardness? Our temporary hardness is caused by your hydrogen carbonates. So your magnesium hydrogen carbonates and your calcium hydrogen carbonates. And don't forget, that's what creates your calcium carbonates, your lime scale, when you do boil off the water. Question 4, suggest a method of establishing the amount of permanent hardness. What you could do is you could first boil your water sample and filter off any temporary hardness that is formed. Then take your filtrate, so that's the thing that comes through the filter paper, it's left in your conical flask, and titrate it the exact same way with your EDTA, carry out your calculation, and you'll be able to calculate your permanent hardness. And finally, the function of the buffer. Guys, if we do not have the buffer between pH of 8 and pH of 10, our air-chrome black tea, so our indicator, will not work properly. And if our indicator isn't working properly, we can't get it as accurate as we would like. Okay, I hope this helps. See you soon.